Hello, in this video we will now look at how to specify the deterministic part of the utility function in order to model the fact that people behave differently. Everybody is different, we have a heterogeneous population, and we would like to make sure that we are able to capture that in the model. That's the topic of this video. So let's consider the variable number k for individual n and alternative I. It's represented by a real number that we denote by z, I, and k. And this real number is associated with a specific unit in order to have an interpretation. As an attribute, it varies both across alternatives, I, and individuals, n. So there are plenty of examples that we can cite. So again, if we look at the example of the transportation mode choice, you can think about auto in vehicle time, which is a quantity expressed in minutes, or the transit in vehicle time, which is also expressed in minutes. You can have the cost represented in cents or dollars or Swiss francs or what have you, or the transit fare in the same units. You can consider the walking time to the bus stop in minutes. So everything is very straightforward. Okay, so if you want to involve a variable, an attribute, which is quantitative and numerical, the only thing you need to do is to think about the unit, which is a natural way to think about it already at the data collection stage, and include this as such in the model. About the unit, what you need to keep in mind is that the utility itself has no unit. Therefore, the coefficient beta of the variable will actually cancel out the unit. So the value of beta will depend on the unit that has been selected for the attribute. So let's take an example. Suppose that you want to include travel time in your model. And you have two possibilities. You can code the travel time in terms of number of minutes, but you can also do it in terms of number of hours. In the first example, where travel time is coded in minutes, the beta 1 has also a unit. Remember, it cancels the unit of minutes, so beta 1 will be 1 divided by minute. In the second specification, where travel time prime is actually the same travel time but coded in hours, well, beta 1 prime now is 1 divided by hour. Both models are completely equivalent. They are exactly the same. It does not matter if you code it in minutes, hours, or what have you. But the estimated value of the coefficient will be different because the units are different. So if you realize that the contribution of travel time to the utility function is the same in the two models, because the ratio of the two travel time is 60 between hours and minutes, well, the ratio between the two coefficients will be also 60. Okay, so beta 1 prime will be 60 times bigger than beta 1. Another important feature that you need to keep in mind when you include a quantitative variable in a specification is to decide if this variable will be generic or alternative specific. What does it mean? Let's compare these two specifications. The top specification, the travel time, is involved in two alternatives. For example, alternative I can be the car, driving by car, and alternative J can be taking the bus. So TTIN is the travel time by car, TTJN is the travel time by bus. And if you look correctly at the specification, the coefficient beta 1 is the same for car and for bus. So it's the same for I and J. In the second specification, we have made a different assumption. We have decided that the impact of travel time on the utility will be different for alternative I and for alternative J. To do so, we have defined two different coefficients. We have the coefficient beta 1, which calculates the impact of travel time on alternative I, and the coefficient beta 2, which capture the impact of the travel time for alternative J. And actually, as we will see later on, you can then test these two specifications against the data and then decide which one is the most appropriate for your context. Now let's move from attributes to socioeconomic characteristics. Well, as you will see, it will be basically the same. So because we are looking at quantitative variables, they are again numerical and continuous. They are represented by a real number that we denote here by S and K. Remember, a characteristic does not vary across across alternatives. I mean, if you take the bus or the car, your age will always be the same, right? So the index is n, the individual. It's again associated with a specific unit, like Swiss francs for annual income or number of years for age. These are the two classical examples of continuous socioeconomic characteristics. Okay, so far so good. It was easy. We take these continuous variables and we include them in the model. We may want to model the fact that they are generic or specific. Let's see if we can go further in the modeling of behavior. An important part of what we want to do is to be able to model the fact that people are different. People have different tastes. People do not react the same way in the same situation. So this is what we call heterogeneity. The population is heterogeneous. People are different, and we would like to be able to model this mathematically in our framework. This is what we will be looking at now. So I write my utility function VIN. And the difference between what I did before and this specification is that I have included an index n to the coefficient. So by doing this, I say this beta 1n, which captures the impact of a variable zin on the utility, this beta in will vary across people. Now the question is, how does it vary? Well, for example, it can vary as a function of income. A typical example is that if zin is the cost variable, the way the cost of a product or an option influence the utility will vary with income. Maybe rich people will be less sensitive to cost than poor people. That's the behavioral assumption. So beta in now becomes a function of a socioeconomic characteristics, like income. This is called interaction. So we are interacting an attribute, which is a variable that describes the alternative, like cost, with a socioeconomic characteristic, like income. So for example, one possibility to relate the beta in and income is to say beta 1n is equal to the product of a coefficient beta 1, which is now generic for all individuals, times income. So now we plug this specification in the utility function to have this. So we have beta 1 times income times z, which is the variable. And actually there is a very interesting way to see this specification. Let's denote income times z, let's denote it by x, xin. So xin is defined as the product of income and zin. If we do that, then we are back to the original specification of a linear in parameter formula. It's beta 1 times a variable. So these interactions can be seen as defining new variables. So in this case, we have defined a new variable, which is the product of income and cost, for example. This is easy to do. You can do it using your Excel or whatever spreadsheet you are using. You include a new column and you calculate this variable based on the existing variable. So you go to this column that you call xin here, and you calculate the product between income and cost, and you have a new variable. And this is this new variable that is in your data file that you include in the model. So this is very flexible. It gives you a way to include complex behavioral reality, capturing the heterogeneity of people, using a simple linear specification by pre-processing the data, by defining new variables based on existing variables. So this behavioral assumption that people have different taste parameters can be generalized. So the difference across people can be characterized by one or several socioeconomic characteristics. So the example that I took where beta 1 was a function of income, well, you could do exactly the same by deciding that beta 1 varies across both income and age. Everything generalizes very nicely. So this is the example. So I define beta 1n as the product of beta 1 times income times age. I plug it again in the definition of the utility function, and I obtain this term. And now, in order to be back to the interpretation of the linear in parameter specification, I define this variable xin as the product of income, age, and zin. And now, my specification is a linear in parameter specification. So again, This more advanced modeling of heterogeneity involving two socioeconomic characteristics amounts to create a new variable, so a new column in your Excel file, that can be included in the model. So this is very flexible. I mean, you can combine all these variables in various ways by pre-processing the data. You can decide to interact several variables together, attribute socioeconomic characteristics, to define new variables and include them in the linear in parameter specification. Okay? So the danger with this flexibility is that you can do anything. Well, you may want to make sure that whatever you do is relevant, so that it has a behavioral explanation. Okay, and in this case, when I took the income and the cost, well, this made sense, right? That the cost parameter would be different for people with different income is something that I can justify from a behavioral point of view. So that's what you need to keep in mind when you do that. You have a lot of flexibility, but you need to make sure that you can justify your specification based on some behavioral assumptions. Actually, if we go back to this cost variable, it's very common to replace the multiplication of the cost by income by calculating the ratio, cost divided by income. The reason why you want to use such a specification instead of the multiplication is that the new variable, cost divided by income, represents something meaningful, is the share of the cost of the purchase of this alternative in your budget, in your household budget. If you go back to the example that we looked at in the beginning of the course, the purchase of an electric car, well, if you decide to buy a Tesla, which is quite an expensive car, well, it may make sense to look at the share of the cost of this Tesla in your income. If you have a low income, this variable will be very high. And if you have a large income, this variable will be lower. So this is a common way to interact cost and income. Interactions can be done with any variable. Okay, you can interact socioeconomic characteristic with any variable, but you can also interact them with the alternative specific constants. So if you remember, the alternative specific constants capture the mean of the error term. And by assumption in the logit model, they should be the same across n because of the IID assumption. But still, we would like to model the fact that they may be different across individuals, and we will use the same trick as for the interaction with normal variables. So if you look at the first specification on this slide, that I call the base model, it's the classical specification where I have included alternative specific constants to each of the three alternatives, except one that I have normalized to 0. Now what I would like to do, like we did before, is to say this beta 1 and beta 2, the alternative specific constants, vary across individuals. So I denote them by beta 1n and beta 2n. And like we did before, I can be more specific about the definition of beta 1n. I can say it's the product between a coefficient beta I and the income of individual n. In this case, we obtain this specification. We obtain the fact that beta 1 income and beta 2 income appears in the utility function. So what you have to keep in mind here is that when you include a socioeconomic characteristic in the model like this, because it's interacting with the constants, you cannot include them in all alternatives. One of them must be normalized to 0, like we do for the alternative specific constant. Now I suggest that you go to the practice quiz, which is provided online, so that you get more familiar with the specification. And then in the next video, we will look into the qualitative variables that will be modeled using discrete variables, and we will see how to do that.